Hi, welcome to Sunil Maths tutorial, Functional Analysis, class number 2. In this video, we learn examples of Banach space. Before going to learn the examples, let us see the definition of Banach space. Banach space is a complete normed linear space. So, what is mean by complete? Complete, every Cauchy sequence in it is convergent. Complete means every Cauchy sequence is convergent. Every Cauchy sequence is convergent. And normed linear space means it satisfies three conditions. Norm x is greater than or equals to 0, and norm x equal to 0 implies and implied by x equal to 0, and norm x plus y is always less than or equals to norm x plus norm y, and norm alpha x is equals to mod alpha into norm x. So Banach space is a complete normed linear space. Now we learn 10 examples of Banach space. Let us see the first example, and which is very basic and trivial. Example number 1. The real linear space capital R and the complex linear space capital C both are Banach spaces. Real linear space and complex linear space both are Banach spaces under the standard norm defined by norm x is equals to mod x for all x belongs to capital C or x belongs to capital R. We prove this example. So let us see, norm x is equals to 0 implies and implied by mod x equals to 0, which implies and implied by x equal to 0. What it means? The first condition of norm x equal to 0 implies and implied by x equal to 0. And norm x is equals to mod x. We know that mod x is a non-negative function. Mod x is a non-negative function. So by using that, norm x is always greater than or equals to 0. Norm x is always greater than or equals to 0. This proves the first condition of normed linear space. Let us see. Let z comma w be the complex numbers, and z bar and w bar are their conjugates of z and z respectively. Now consider z plus w whole square. Z plus w whole square. We know that in the complex space, z square can be written as z into z bar. We know that mod z square or simply z square can be written as z into z bar in the complex analysis. By using that fact, z plus w whole square can be written as z plus w into z plus w whole bar. Again we know that z plus z1 plus z2 whole bar is equals to z1 bar plus z2 bar. By using this fact, here it can be written as z bar plus w bar. Now we multiply with one another, z into z bar, z into omega bar, w bar, w into z bar, w into w bar. So we get this step. Again by using this fact, z into z bar is equals to mod z square. So this is clearly like mod z square, z into z bar is equals to mod z square, w into w bar is equals to mod w square. Now we use the fact that z into z bar plus z into w bar plus w into z bar is can be written as 2zw. 2zw. That's why we replace equality by inequality. Equality by inequality. Because of we know that by complex numbers theory, z1 plus z1 into z2 bar plus z1 bar into z2 is always less than or equals to 2z1 into z2. 2z1 into z2. That's it. So this step, that's why we write here this equality becomes inequality. Now by using this RHS, this is in the form of a square plus 2ab plus b square. So which is less than or equals to a plus b whole square. It means mod z plus w whole square less than or equals to mod z plus mod w whole square. By removing squares on both sides, we get mod z plus w less than or equals to mod z plus mod w, which is the second property of normed linear space. And the third property, norm alpha x is equals to, by definition of norm, it can be written as mod alpha x, and mod alpha x can be written as mod alpha into mod x, where alpha is a scalar. This shows us the set capital R as well as capital C both satisfies the three properties of normed linear space. Hence, we conclude that C and R both are normed linear spaces. And we know that both complex numbers and real numbers are complete. Therefore, they are complete as well as normed linear spaces. C and R both are complete as well as they are normed linear spaces. Hence, both C and R are Banach spaces under the standard metric defined as norm x is equals to mod x. If anybody wants to prove of set of complex numbers and set of real numbers are complete, please message under the video, then I provide the proof for that. Let us see example number 2. Again, this is also one of the standard example. The linear spaces R power n and C power n. The linear spaces R power n and C power n. This power n represents the set of all n tuples. The set of all n tuples like this. X is equals to x1, x2, and so on, xn. Of real and complex numbers, both are Banach spaces under the norm defined by norm x is equals to square root of x1 square plus x2 square plus and so on plus xn square. This norm can be simply represented like this. Summation over I is equals to 1 to n xi square whole power 1 by 2. This R power n is called Euclidean space and C power n is called unitary space. We go for example number 3. Again, one of the standard example. Let P be any real number such that 1 less than or equals to P less than infinity. P is a real number and it is 1 less than or equals to P less than infinity. This LP power n, standard notation, LP power n be the set of all n tuples which are consisting in the swarm x is equals to x1, x2 and so on, xn of scalars. This LP power n also a Banach space under the norm x power p is equals to summation over I is equals to 1 to n xi power p mod xi power p whole power 1 by p. This is nothing but mod x1 power p plus mod x2 power p plus and so on mod xn power p whole power 1 by p. Again, so LP power n, the set of all n tuples which are in this form, is a Banach space under this norm. We go for next example, example number 4, which is also in the similar manner as example 3 with a small difference. Again, P be a real number and 1 less than or equals to P less than infinity, and here LP is the space of all sequences. Here LP is the space of all sequences. X is equals to x1, x2 and so on, xn and so on. In the previous example, they are n tuples, but here they are infinite. They are infinite in number of scalars, satisfying the condition summation over I is equals to 1 to infinity x power n whole power p is less than infinity. It means it is a finite quantity. This summation n is equals to 1 to infinity mod x power n whole power p is a finite quantity. Then this space LP is a Banach space with the same norm defined as above. Norm xp is equals to summation n is equals to 1 to infinity mod xn power p whole power 1 by p. This example holds for all positive. Real numbers. If you replace this n by p, then you get like this. If you replace, not n by p, n is equals to 2. I'm sorry, not n or n equal to 2. If you replace this p is equals to 2, you get norm xp in place norm x2 is equals to summation over n is equals to 1 to infinity x2 xn power 2 whole power 1 by 2, whole power 1 by 2. So this example, from this example you construct many more examples. Instead of, in place of p, you can replace 2, 3, 4, 5 like that and so on. This theorem can be very helpful by using, Rice-Jet representation theorem. This LP is complete by using Rice-Jet representation theorem, Rice-Jet-Fisher theorem. In the upcoming classes, we prove that theorem also. Example 5, and one of the more important example for our examination. Let us see the linear space C of all convergent sequences. Observe that C is the set of or linear space of all convergent sequences x equals to xn with the norm x is equals to supremum of xn. Supremum of xn. Supremum of the sequence xn such that is a Banach space. So the set of all convergent sequences defined with the norm forms a Banach space. We prove this example because of its importance for our examination. Here observe that we define the norm as norm x is equals to supremum of the sequence. Norm x is equals to supremum of the sequence. First we show that it is a normed linear space, and then we show that it is a complete. It satisfies the completeness property. It means every Cauchy sequence in it is convergent. Right. Mod xi is always greater than or equals to 0. So obviously norm x is greater than or equals to 0. Norm x equals to 0 implies and implied by definition supremum of xn is equals to 0. If supremum of the sequence is 0, then each term xn equal to 0. It means x equal to 0. So norm x equal to 0 implies and implied by x equal to 0. This shows us the first condition of the normed linear space. First condition of the normed linear space. We go for second condition. Let us take x is equals to sequence xn, y is equals to sequence yn be two elements of C. Remember that C is the space of or collection of all convergent sequence. All convergent sequences. Now x plus y is equals to sequence xn plus yn. Now by definition of norm x plus y is equals to supremum of xn yn, where you can write 1 less than or equals to n less than infinity. It is obvious. So this equality becomes inequality by splitting the supremum. Supremum of xn plus supremum of yn. What is supremum of xn? Norm x. And what is supremum of yn? Norm y. This shows us norm x plus y is less than or equals to norm x plus norm y. This is nothing but second property of normed linear space. Second property of normed linear space. We go for third one. Consider alpha is any scalar. Now norm alpha x is equals to supremum of mod alpha xn. By the properties of supremum, it can be written as mod alpha into supremum xn, mod alpha into norm xn. This condition shows us third property of normed linear space. Hence we conclude that this set satisfies all the three properties of a normed linear space. Therefore, capital C satisfies all the properties of normed linear space. This shows us C is a normed linear space. Now we have to prove that this C is complete. We have to prove that this C is complete. What is mean by complete? Every Cauchy sequence in it is convergent. So right, now define a Cauchy sequence in it. X power n be a Cauchy sequence in C. X power n be a Cauchy sequence in C. Then this xn can be written as x1 power n, x2 power n, x3 power n and so on, xi power n and so on. We assume that C is the set of all convergent sequences. The set of all convergent sequences. Obviously by using that example, by using the definition, capital C consisting of all convergent sequences. So by definition of C, for each epsilon greater than 0, there exists a positive integer n naught satisfying the condition x power n minus x power m is less than epsilon. This is less than epsilon. This condition is written by the definition of, we can take epsilon by 3. We can take epsilon by 3. Instead of epsilon, let us take epsilon by 3. X power n minus x power m is less than epsilon by 3. I'm sorry. This inequality can be written by using the definition of Cauchy sequence. By using the definition of Cauchy sequence. So right after that, norm x power n minus x power m is less than epsilon means, epsilon by 3 means, by the definition of norm, supremum of over I, xi power n, xi power m is less than epsilon by 3. Is less than epsilon by 3 by applying the definition of the norm in this example. Hence, for each fixed I, the sequence of real numbers xi power n is a Cauchy sequence in capital R, and we know that capital R is complete. Capital R is complete means every Cauchy sequence in it is convergent. This shows as the limit xi power n is equals to xi for each fixed I. Now we fixing n greater than n naught and letting m tends to infinity in the above inequality xi power n minus xi power m less than epsilon by 3, we get xi power n minus xi is always less than epsilon by 3. This shows us supremum of xi power n minus xi is less than epsilon. This shows us norm x power n minus x tends to infinity as n tends to infinity, where this x is equals to the sequence xi. Now it is remaining to prove that x belongs to capital C. The limit of the sequence also belongs to capital C. It is enough to show that it is a Cauchy sequence in capital R because it consists of all sequences which are convergent. So now xi power n naught is equals to xi power x1 power n naught, x2 power n naught and so on xn power n naught is a convergent sequence. So xi power n naught is a Cauchy sequence. Apply the definition of Cauchy sequence. You get xi power n naught minus xj power n naught is less than epsilon by 3. Now you can write like this. Xi minus xj is equals to xi minus xi power n naught plus xi power n naught. I add and subtract the same terms. Similarly, xj power n naught minus xj power n naught. By splitting the terms, this equality becomes inequality norm x minus x power n naught plus norm mod xi power n naught minus xj power n naught plus norm x power n naught minus x. By previous argument, we have all these inequalities less than epsilon by 3 plus epsilon by 3 plus epsilon by 3. Every term is less than epsilon by 3. So by using equation 1. Hence we conclude that mod xi minus xj is less than epsilon. It means this xi is a Cauchy sequence in capital R. If this xi is a Cauchy sequence in capital R, obviously this x belongs to capital C. This shows us every Cauchy sequence in C is convergent. Hence, capital C is complete. This condition shows us capital C is complete. Already we proved that it is a normed linear space. Now we show that it satisfies the completeness property. Therefore, C is a complete normed linear space. Hence, C is a Banach space. Remember that this example is, proof of this example is lengthiest one, and go through it carefully. So I repeat the statement of this example. Observe that the linear space C of all convergent sequences x is equals to xn with the norm x is equals to supremum of the sequence xn such that where 1 less than or equals to n less than infinity is a Banach space. Now let us see example number 6. Example number 6. Closed interval a comma b is a bounded and closed interval. Then the linear space C of closed interval a comma b. This symbol represents the set of all continuous functions defined on closed interval a comma b is a Banach space with the norm f is equals to supremum of f of x, where each x belongs to closed interval a comma b. This C of a comma b, this is important. C of a comma b, C of closed interval a comma b means the set of all continuous functions defined on the closed interval a comma b is a Banach space with the standard norm supremum of f of x such that x belongs to closed interval a comma b. And let us take one more example, example number 7, C of x. C of x, remember that, where x is a compact metric space, where x is a compact metric space, it satisfies the compactness property. C of x be the set of all continuous real valued functions. C of x be the set of all continuous real valued functions defined over the compact metric space capital X. This is also a Banach space with the norm defined by norm f is equals to supremum of f of x such that x belongs to capital X. It means the set of all continuous functions defined over a closed interval by using previous example. The set of all continuous real valued functions defined over a compact metric space, both are Banach spaces with the metrics defined in the same way. The main difference in the examples is here the closed interval a comma b, here the compact metric space capital X. That's it. We go for next one and depends upon topological space. C of t. C of t. The set of the C of t denote the linear space of all bounded continuous real valued or complex valued. Remember that. C of t denotes the set of all bounded continuous real valued or complex valued functions over a topology capital T, over a topological space capital T. Then C of t is also a Banach space with the norm f is equals to supremum of mod f of x where x belongs to capital T. In the example number 6, 7 and 8, you observe the difference. In first example, we choose a closed interval a comma b, example number 6. In the second one, compact metric space capital X. In the third one, we use the topology T, but the nature of the norm is same, supremum of mod f of x. We go for example number 9, which is a measurable function. Let capital X be any measurable space with measure mu. X is a measurable space with measure mu and P be any positive integer. Then LP consists of all measurable functions. Then LP consists of all measurable functions defined on capital X such that f of x power p is integrable. Remember that LP is the set of all measurable functions defined on capital X such that each measurable function is associated with another function f of x which is integrable. Then LP is also a Banach space defined by the norm f is equals to integral over x mod f power p d mu whole power 1 by p. On last example, observe that consider the linear space of all n tuples x is equals to x1, x2 and so on xn of scalars, and the norm is defined by norm x infinity. Norm x infinity is equals to maximum of mod x1, mod x2 and so on mod xn. Then this linear space is a Banach space and it is denoted by L infinity power n. L power n infinity, norm x infinity. So observe that in this class we learn 10 examples of Banach space, and we prove 2 examples, example number 1 and even example number 5, and we state some examples over the closed interval a comma b and over a compact metric space capital X and a topology capital T, and also we see an example over measurable functions also. So from these 10 examples you can understand Banach spaces, various Banach spaces over different types of functions. So I conclude this class. In the next class we learn some inequalities according to functional analysis. All the best.